Thank you very much, Kurush. As I was just gossiping, I regret that I wasn't able to come, but you can still listen to a little bit about higher order normalization group equations. And I'm just to represent this, going to draw a quick cloud to say that this is a little bit light compared to what we've been hearing about the last little moment. If I'd thought ahead and realized I was going to be on Foundations Day, I might have said something a little bit different. My own thoughts in Foundations are maybe more in the direction of what we heard in passing about the value, that the larger value that perhaps people realize that formal series and trans series can play in the Foundations story of quantum field theory. But I'm not going to talk about that. I'm going to talk about something else. This is joint work with a pre-COVID master's student of mine, William Dugan, and Loïc Foissy. And well, so this is a little bit old. There was supposed to be a paper out of his master's work that got much delayed by COVID and still does not exist. But I thought I would speak about it because it has a lot of words that intersect with the workshop title, although, as you will see, not in quite as deep a way as you might hope. So what's the story? I think most people in the audience know about the Convolution algebra, but just because I think it's really valuable when people from outside the community are welcome. And so I want to just very briefly tell you what the Convolution algebra of rooted trees is. So we're going to start with a set of rooted trees, and I want to not allow an empty tree for the moment, although the empty tree will appear very shortly. And then what I'm interested in is the polynomial algebra on these rooted trees, and there immediately the empty tree comes back because we can reinterpret monomials in this polynomial algebra as forests, so that the multiplication becomes disjoint union, and then the empty monomial becomes the empty forest, and thus also the empty tree. Then what happens next? Well, to make this into a Hopf algebra, we need to have a coproduct. And what is our coproduct going to look like? We're going to take a sum over subsets of vertices of the tree. And then what are we going to do? We're going to take the product of all the guys that you get that are rooted at the elements in your set. And then you're going to have everything else. And I'm going to write everything else as a subtraction, but those of you, who's almost everybody, knows that in fact, it's better to think of it as a contraction, and in particular, because if you get nothing, you would like to see this be 1, not 0. And so just to say, what is TV? TV is the subtree rooted at V. And then this is my way to write it, which nobody else really quite writes it this way, but I like it because the two parts of the primitive part occur quite naturally. But that does lead to this weird convention that I want to see this as 1 when empty. Okay, that's all. The rest as it needs to be. So I think you're all aware of this, and we will just only very quickly do an example where if we have this guy, what subsets can we? Oh, sorry, but I missed the important thing, that S has to be an anti-chain. That's the key thing that I didn't write down for some reason that was not a good one. So what does this mean in this context? What are the anti-chains? Well, you could take just the root and use that convention. You could take nothing at all and get this guy. You could take either of these isolated vertices, or you could take both of them because that's an anti-chain. And that's your Konkheimer-Hopf algebra. Okay, what am I going to do with it? Again, this is also an old piece of the story that I know many people have seen before, but it's underlying what I do want to say about renormalization group equations, is that we can build what in a symbolic or enumerative combinatorics world would be called maybe tree specifications. We can build them with what are essentially the Dyson-Schwinger equations for from a quantum field theory. And to do that, I need B+, which is the notation in this community for the add a root operator. So I'm just going to make a new tree like this. And then this is exactly the operator you need to build tree families and what you would maybe call simple tree families or simple tree classes. So for example, I've got 2 simple examples here. What's this first one? Well, let's just expand it out and see what happens. I don't know why that little guy that showed up there. Well, so if I do b plus, if I plug the series back in, I do b plus of just 1. Well, that's just putting a root on nothing at all. So that gives me just a root. Okay, I'm having a not so good technical day here. And now what if I plug this all back in again? What am I going to get for the x squared term? Well, I've got the x from here. I've got the x from here. So I have to take b plus of this guy, which is this guy. And I think you can see what's happening here. What's the next term going to be? It's going to come from b plus of the x squared term. And so we just get ladders. This is a very simple example that gives ladders. And because I'm going to need it later on, I'm going to call Li the ladder with I vertices. Okay, what's another example that's slightly more interesting? We could do something like this. What's this going to do? Okay, well, it's got a 1. I think I'll put my minus sign in already. Now, what's going to be the coefficient of x? Well, I have to put 1 over 1. Okay, that's just 1. I have to take b plus of 1. Okay, so that's the same. That was boring so far. And now what do I do next? Well, I've got this thing here. I want to put it in here. It's a geometric series. So I'm going to expand out the geometric series. And so now I've got for the x squared term, I shouldn't have put the plus sign there because what am I going to get? I'm going to get b plus of this guy. And so there's still this outer minus sign. And so you get something like this. And what's going to happen at the next order at x cubed? Well, in my geometric series, I have this guy that I get to b plus. So I do have that one. And then I also have the result from the squaring this whole thing. The x squared term is 2 of these. So I also get this and so on. I'm going to write the x4 term. If you haven't seen this before, you should think about what it is as I'm writing it or before I write it. But I know that many people have seen this before, so I don't want to belabor the point. And goes on. And you can say, okay, well, what are the coefficients here counting? And what they are counting is the number of ordered rooted trees with that unordered structure, or you might say plane rooted trees, the number of plane embeddings of that rooted tree. And so the 2 here is because of the fact that if I'm looking at ordering the children, I would have this guy and this guy, and together they give the 2. So this is just counting ordered rooted trees. That's all. And so these give tree specifications. Why do they have anything to do with Dyson-Schwinger equations? Well, the idea, as again, I know many people know, but for those who haven't seen this part of this game before, we're using the trees to represent subdivergent structures in Feynman diagrams. And so when you're building a building like this, you're building by inserting subdivergences into some sort of skeleton graph, and that's exactly what's going on diagrammatically with a Dyson-Schwinger equation. And in this context, if you want overlapping divergences, you need to have a sum of trees, but for the moment, we're not worrying about that. We're going to play some pure tree games today. Okay, so to take the next step, we want to think about what the Feynman rules would be in this context. And so what is this going to look like? And this is one of these things that I just never have I never have the most beautiful notation for it, but I don't think the idea is so bad. So we want some map from our trees into some target algebra, and my target, oh, that's meant to be not that Q, that's meant to be a rational numbers Q. Oh, wrong Q. Okay, it's just for me going to be just polynomials in some L, which is my log energy, my log Q squared over mu squared, or whatever you want it to be, because I'm going to work in a single scale context, or sort of modeling a single scale context. And as you know, many of you know, I do various other things with Dyson-Schwinger equations that are actually of Feynman diagrams, and I do typically work in a single scale context. Okay, but then algebraically, what properties do we want our Feynman rules to have? Well, the classic thing, we want them to be a character or an algebra homomorphism in this context. If we were working on the original Feynman diagrams, we would probably want some sort of multiplicative property on bridges so that we can move to 1pi in the usual way. But here in this tree context, we're sort of already modeling insertion structures of 1pi diagrams. So that's already built in. And then what is the other thing that we want? We want it to somehow behave well with respect to the coproduct. And the specific rule that we want is this convolution rule. And I never quite know how to write it neatly because I'm doing a substitution. I'm trying to notate a substitution of the L variable, which is otherwise sort of not in the notation. So that's a kind of gross notation for saying, look, if you take the Feynman rules where the variable is L1 plus L2, that's the same as taking the convolution of the Feynman rules with the L variable being L1 and the Feynman rules with the L variable being L2. So yeah, that's all that I'm trying to say. And the convolution, if you haven't seen this part of the hop game before, just means take it apart with the coproduct, apply the two maps, and put it back together. So if you're algebraically minded, you might even actually call this the renormalization group equation. Sometimes people do. And you would also see that essentially what we're talking about is the Feynman rules have to come from the exponential map, or they sort of are almost the exponential map. And I confess that not being as algebraically minded as some of you, I didn't actually realize that right away. Fortunately, you can work it out by hand, and then you will see exactly what you would get out of the exponential map. And I personally like doing things concretely sometimes. So let's work out exactly what the most general tree Feynman rules can look like. Let's first just talk about what the leading behavior is going to be. And that is the following, where you take a tree and you map it to L to the number of vertices of the tree. So the size here is number of vertices, which is the usual grading in the Konkheimer-Hopf algebra, divided by the tree factorial. Okay, so what the heck is the tree factorial? So the tree factorial, you have to take a product over the vertices, then the number of vertices in the subtree rooted at V. So that's kind of nice, and it's behaving like a factorial. Again, if you haven't seen this before, the question you should be asking, and which I will answer for you in just a moment, is what tree gives the regular factorial when you take its tree factorial? Okay, and the tree factorial, not necessarily with this notation, it's also a very nice classical thing. It's known, it's an exercise in Knuth, in fact, that it counts the number of increasing, well, the size of tree factorial the size of the tree factorial divided by the tree factorial counts the number of increasing labelings. And that's what's an exercise in Knuth and a sort of standard fact. And then recursively, you can work out, in fact, what the most general tree Feynman rules have to be, and it's just also what you would derive from the exponential map. And what do? You take, if you have a forest, you take any subset of the edges, and you are interested in two different things. You're interested in the forest that's made of, oh, I've got capital and lowercase f's. That's one nice thing about writing is I can correct typos. So if I take the forest and just remove those edges, that gives me a different forest, or typically different forest, unless I have the empty set here. And I do still need to have some rule for what the trees of that forest give me. And I've called it sigma suggestively, that it's coming from taking the infinitesimal character. And then I'm left with, you take sort of the rest in an appropriate sense, and you take just the tree factorial Feynman rules on the rest. And that's all it can be, which is kind of what you would expect, because here you're taking off pieces by repeated coproduct and going from there. Okay, well, that's all fine and good. What about the renormalization group equation? Well, what's the renormalization group equation? You guys all know what the renormalization group equation is, but let's write it down in this context, because there's a number of different ways that it can look. And in fact, we already saw one of them. You can think about that rule that I was treating as a defining rule for what should count as Feynman rules. You can think of that as the renormalization group equation. But if we want to write it a little closer to how you might see it in a physics textbook, let's think of it like this. If we apply our Feynman rules to the combinatorial Dyson-Schwinger equation, well, what's that going to give? That should give physical Dyson-Schwinger equations. And so the thing that you're getting, the solution, will be the Green's function. And I'm going to call it GXL. It's going to depend on the L variable and my X, which is playing the role of the coupling. And then what does it satisfy? This is the renormalization group equation. Because what is it telling us? It's telling us how the L derivatives and the X derivatives relate via a beta function and an anomalous dimension. And all of the examples, the two examples up there do in fact satisfy the renormalization group equation for appropriate beta and gamma. And in fact, everything you can build out of the kind of Dyson-Schwinger equations, I didn't write down what I'm going to consider the general form, but anything you can build out of Dyson-Schwinger equations will automatically satisfy this renormalization group equation, which makes sense because those are all systems that you can get in some physical sense, and so they should satisfy the renormalization group equation. And another way of saying that is that the Feynman rules, there's a triangle between the Feynman rules, the renormalization group equation, and the Dyson-Schwinger equation. And so anytime you have two of those, you sort of get the third one in a way that I don't want to make completely precise at the moment. But I think it is useful to think about any two of those giving the third. Okay, well, now let's do something kind of silly but fun. Let's allow hired x derivatives. So if I go back here for a moment, one thing I could imagine doing this is solving it for the d by dl part, right? I could just write it, it's just sort of silly, right? I could just write, well, d by dl is equal of g is equal to the rest. Okay, what's the rest? Beta of x, d by dx minus gamma of x, g of xl. Okay, that was kind of trivial, but that's one way to think about the renormalization group equation. Is it tells you that if you're taking L derivatives, really all you need to know is about G and its X derivative. Okay, well, let's allow higher X derivatives. Okay, and we would get something like this, and we would say if a Green's function satisfies this equation for some beta that's a polynomial in its second argument, so I'm only going up some polynomial in the x derivatives, then we'll say it satisfies some generalized renormalization group equation of order the degree of beta bar in that argument. Okay, and I said all fault is mine. So these arose quite a long time ago from some conversations. I was visiting Dirk and Spencer Bloch in Chicago, and we were chatting about some things, and somewhere along the way I was like, oh, well, what about this? And they're like, well, I don't know, I don't really care. No, I don't think that's exactly what they said, but all fault is mine, because if you're sitting there and you're like, I'm not sure I know any physical examples of that beyond the normal renormalization group equation, well, you may very well be right, but there's still some kind of neat mathematics, and I think we'll see in a moment a little bit about why your physical intuition tells you that too. Okay, so all fault is mine. Okay, what else? Well, let's go back to the two examples and see what happens with them. I already told you they're all going to satisfy the original renormalization group equation, but let's just look at what it looks like in this context. Okay, so we've got this original guy, and remember what that looked like. It looked like just these ladders, right? So we have ladders. And so to understand what's going to happen, we need to look at what is the coproduct on a ladder. There's the ln, just to keep my notation slightly nicer. Well, what is the coproduct on a ladder? Well, the only anti-chains of vertices I can take are single vertices. So this has a very easy form. Okay, and what we're going to need, what we're going to do is we're just going to encapsulate these coefficients in a little array, and we'll see it better with the next example. So in this next example, let's actually work out some of these coproducts. So I guess I'm going to go back up here, and I'm going to just cut out and collect this series, and then I'm going to take it down and work with it. Maybe I'm not, because I've changed where my all my things are, and I lost where my cutting is. Is it this one? So there we got this guy, and now I'm going to start taking coproducts. Okay, coproduct of 1, that's just 1 tensor 1. Coproduct of dot, that's 1 tensor dot plus dot tensor 1. Okay, coproduct of this guy. Well, there's always the primitive part. There's also one more term, which we already saw up above, since that is in fact a ladder. What about this guy? Well, there's always the primitive part. And then what else is there? Well, I could take off just dot. And if I take off dot, I can take it off in 1, 2, 3 ways. And all of those ways give me that. So I have a 3 here. What else could I do? I could take off the little stick. And there's only one way to do that. So I get that. All right, one more. I am not going to draw the thing every single time. I'm going to call this A4. Okay, so there's always the primitive part. What else is there? How many times can I take off dot? Well, I can take off dot from here. I get this triple stick. I can take off dot 2 times from here. I get this triple stick, and here and here. So I've got 5 ways to take off dot and get a triple. Okay, how many ways can I take off dot and get just the little V shape? Well, 2 from here and 3 from here. So I also get 5, which you knew had to happen by an old result that these guys always generate a subhop algebra. So that's nice to know. What else could we take off? Well, I'm not going to bore you with it, but I could take off 3 copies of that little stick. And I can also take off this guy. Oh, and I forgot something again. You guys aren't catching all the mistakes I make. That's one of the problems with Zoom. But we'll go fix it in a sec, because there's also stuff here. And I don't care about the stuff, which is why I forgot to write it down. And I'll show you why I don't care in a moment. So what is the stuff that I don't care about? The stuff I don't care about is actually is a forest. It's actually a product on the left-hand side of the tensor. So not a single tree on the left-hand side. And I don't care about that kind of stuff right now. Which again, if you're thinking in an abstract sense, this should not be too surprising, because if we're moving to the Lie algebra and we're linearizing, we don't really care about that stuff, right? So I want to capture what does matter. And what does matter are these coefficients. And so what we got a nice 3 here, we got a 5, we got another 3. These are really all 1s. There's lots of 1s here, 1s. This one really is a 1, etc. And so I just want to put those coefficients into a little array. Now I threw away the signs, so if we want to put the signs back, we want to actually write everything in terms of these coefficients and put those into this matrix. What are we going to get? Well, 2 1s get a 1 here. These have to change sign because the dot needs to change sign. So we get something like a -1, -1. Continuing to go along, we're going to get something like this, -1, -1. But this one, those are both the same sign, so that gets to go away, and so on, right? So I'm going to do it this way. So I'll get a 3, a 1, -1, -1, 5, 3, 1, -1, and it would go on. If you did the same thing up here, you just get all 1s, etc. So what are we seeing here? And I'm not going to go through all the details of the calculation that shows this. You're welcome to do it yourself. These satisfy what in this way of talking about it would be a 0th order renormalization group equation, i.e. an equation with the beta function equals 0. So that's, you knew from the beginning that ladders were kind of trivial. They have a pure scaling solution and blah, 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 because they're just ladders. And when it's a 0th order renormalization group equation, when you make this matrix, you see these sequences are all just constants. Now, in the next guy, what do we have here? Maybe I'll stick with this color. I claimed that this also had a renormalization group equation, but this isn't a beta function equals 0 situation. This is like a 1-loop propagator diagram inserted into itself on one of its internal edges in all possible ways, including iterating along and nesting. And so that, that's a very classic example, which I'm sure you've heard other people talk about at some stage. Gerald Dunn at least talked about an example that had that form. And so, it's going to satisfy non-trivial from a normal physics perspective, renormalization group equation, so it's going to be first order. And in fact, we see that represented here. Well, I didn't really draw enough of them to convince you, but if you actually do the calculation, you will see that the fact that the renormalization group equation was first order is the fact that these sequences going down this way are first order sequences, in the sense that there's a constant difference being added on in that way, or they're values of a linear polynomial. Okay, and sure enough, in general, that's what's going to happen. So in general, if I write the coproduct in terms of just keeping that linear part, so I'm going to write this as a sum, I equals 1 and minus 1, and there's some lambda I, and I think if I didn't copy the indexing incorrectly, it should be like this, Tn minus I plus stuff, and this is the same kind of stuff, which is products in a non-trivial way, and then I'll get a Ti. Then sure enough, what I want to talk about is what happens when we look at the array of these lambdas and we look at the order of those leftward diagonal sequences. All right. And now I'm going to do one other slightly weird thing, is I'm actually going to crop out those outer ones or minus ones. So I'm going to only think about this piece. This partly comes from, if I'm thinking of it really as like a sequence of trees, then but the empty tree is sort of in there automatically. So I'm going to think, if I think of it as a sequence of trees and I'm not thinking about the empty tree, then I'm most interested in that sort of inner part. And so that's what I'm actually going to use from now on. I'm going to say that a sequence of these Hopf algebra elements that are homogeneous of degree I and that generate a Hopf subalgebra. The algebra that they generate is a Hopf subalgebra. Then I will say that it's kth order if, when you write out this guy, you get kth order sequences on all of those leftward diagonals. Okay, so at some level that was all motivation. I said some things about some renormalization group equations, and I added some more derivatives in X, and I said, oh, let's think about what this does. And now I've turned it into just a tree question. Incidentally, these ones I'm going to call strong, and I'll see why in a moment. But first, let's just stick with this and think about what we can do with it. Because now you can walk out of this conference, which is about physics, and renormalization and things like that, and you can go walk into a room with pure combinatorics people and say, hey, I'm interested in sequences of trees that have this property. And then you can see what you can tell about it. So let's see what we can tell about it. Zeroth order is fairly straightforward. So this was these guys. I forgot that I was going to give them a name. So these are the L's, log 1 plus sum of the LIs. And I'm just going to, if I take the logarithm of that, I'm just going to give a name to the coefficients. And then what it turns out, the only thing that can happen at zeroth order is I basically try to undo this logarithm, but maybe I allow myself to truncate somewhere along the way. So I take either a finite sum of p's plus the next p with a possibly different coefficient, or, well, look, that's a kind of silly way to write it. That's just the ladders again. And in terms of the zeroth order, in terms of the triangles, what are those going to look like? It's either just all the ones, as we saw before, that was the ladders, or it's ones for some certain distance, and then it's some other value b, and then it's 0 all the way after that. And that's all that can happen at zeroth order. So, I mean, it's slightly a lie to say that it's only ladders, because when you play this logarithm game, if you've thought about the primitives in these algebras, you know that that's building you some primitives, and fine. But in any case, it's basically made out of ladders. Okay, what about first order? And I don't think anyone has probably no one has heard my student William talk about my ex-student William. He's now doing a PhD at UMass Amherst with someone else. Anyway, this is the one part that's a bit new for any experts who are here, is that we did finish working out the first order cases. And what do they look like? Well, here's 3 of them. And let me just point out a few features as we're going through. So you will see, what do you see here? I see some binomial coefficients, right? Like that's actually j plus 1 choose 3, right? That's nothing too crazy. So there's some binomial coefficients. Well, this is actually a very small binomial coefficient too, isn't it? And if I go down to the next page, well, look, there's j choose 2. So I see some things that are built out of some initial cases, and then everything else is built from there using some little expression with binomial coefficients. Okay. And you sort of see there's some different sort of jump factors, if you want, here in how they relate. There's 2s and 4s and things like that. And then there's this last one is a little bit extra trivial because it has an awful lot of zeros in it. And that's it. That's all you can get for first order, strong first order. So that's just satisfying the renormalization group equation in the normal way, with that one extra caveat that we cut out the outside part of that array of lambda values. So this is slightly more general than the normal physicists' version of the normalization group equation, but only a little bit. And this is what you get, these 5 cases. Okay, and some of these cases you already know. So this E case is Corollas. So, okay, what are Corollas? I better tell you what Corollas are. Corollas are, you have a vertex and you have, it has children, and that's it. So I would tend to call these fans. It's another thing you might call them, or brushes or something like that, but these guys. Now, so that's case E here. Case A, if A1 equals A2, you go back here. So there's there's 3 parameters here. There's A1, A2, and there's B. And if A1 equals A2, then you get everything from Dyson-Schwinger equations. And by everything from Dyson-Schwinger equations, I mean, you go to the nice characterization that Loïc Foissy did quite a few now years ago of all the things that are Dyson-Schwinger shaped and give a Hopf subalgebra. You get this 2-parameter characterization, and that's exactly what you're getting out of here. So that's all the Dyson-Schwinger cases. Here's another case that is combinatorially kind of pretty. If I set A2 equals 0 and A1 not 0, so if I set just the A2 equals 0, so then notice it's not quite Corollas anymore. There is stuff here, right? It's not as simple, but I've thrown away the part that's somehow changing or doing anything interesting. And so what I end up getting in this case is a family of weighted ladders with extra leaves. So what do I mean by ladders with leaves? I mean that there's a ladder, but it's allowed to have more leaves. But there's at most one vertex at each level that has a child that's not a leaf. Another term you might see for something like this in the literature is caterpillars. But notice they're caterpillars where they're actually rooted at one end of the caterpillar. It's not just a caterpillar tree where you can root it anywhere. You have to root it at one end. And so if you do that, you get, you can write that as a nice expression of the sort we've been working with before. And in fact, you can calculate exactly what the weights are. They have to do with taking A to the power of the number of leaves. I guess it's A1 to the power of the number of leaves of the tree. And the B is to the power of the depth. And there's an extra factor. So, you know, kind of cute. And that's it. So the only thing that's this strong higher order is actually scaled Corollas. And you say, well, I knew this at the beginning, Karen. Why did you make a definition that looked physically kind of silly? And then you tell me that I do a bunch of math and then there's nothing there. Well, that was kind of silly. Okay, so let's just first talk about what I mean here, that these are the only strong higher order sequences. And then we'll talk about how it's still not completely silly. And I hope we had some fun along the way, and maybe there's even something to learn from it. So what do I mean by scaled Corollas? So if you remember the original Corollas, or the zero, or whatever, the original, I mean, what are the Corollas? There's this, we get something just like this, something along here and all zeros elsewhere. But I wrote these coefficients all as one, but actually they could be kind of whatever they like just by adjusting the coefficients in the sequence at the beginning, right? Because if I have this guy and then this guy and then this guy and then this guy, well, when I'm calculating this coefficient, if you remember in the coproduct, how do I get that coefficient? It's by, I want to say, well, how many ways can I cut off a leaf or a single vertex to get the previous guy? Well, that's all I can do here. All I can do is cut off a single vertex and get the previous guy. And if I just do it naively, well, there's just n, right? So I get 1, 2, 3, 4, 5, 6, right? Okay, and that's why it's first order. That was our example E, sort of the natural Corollas. But I could make it 0th order just by doing something, oops, not that, just by putting in coefficients that are the correct coefficients. If I put in these coefficients, now suddenly it's a 0th order sequence. Okay, and if I put in some other coefficients that were growing, then it would be a higher order sequence. So the point is, it's higher order, but in a kind of stupid way. So that's scaled Corollas. And the reason it always works is because it forces zeros here, so nothing can go wrong in the other sequences. Okay. But in my last 2 minutes, let me tell you something. I mean, this was your conclusion. You're like, you just spent 40 minutes telling me about something that was not quite the right notion. But it's still an interesting notion. And the suggestive case is the Convolution. So this is, again, something that's been around for a long time, but it's still very nice. It's built by natural growth. So we start with just dot. And then we say, well, how many ways can I grow the dot? Well, I could grow it 1. I get that way. Now, I could grow it either, add a new leaf at either of these vertices. So the next order, I get this. Okay. And then what happens at the next order? Well, it's almost the same as the plane weighted rooted trees, right? Because I could grow at the bottom there. I could grow at the next vertex up. I could suggestively leave a space and grow at the root. But now on this last guy, well, I could grow that guy at its root or either of its leaves. So I get 3 of these, and so on. Okay, so the only difference so far is this coefficient from the plane rooted trees. And as you go up, you will see further differences of coefficient. And if you start to calculate out this guy, well, what does that 3 start to affect? So before we had this sequence that went 1, 3, 5. And when we got the 5, there were 2 from here and 3 other ones. Now there's 3 of these. So this 5 is going to turn into a 6. And if you haven't seen this before, I invite you to maybe calculate another and see what the pattern is. Or it's also not too hard to prove that what this is really doing is going by binomial coefficients. These are all, in fact, this whole array is full of binomial coefficients, and these ones are n choose 2s. N choose 2. Okay, well, that's quadratic. Isn't that nice? So here's an example of something where we get a quadratic sequence, and you say, aha, there's something kind of second order about Convolution. And I think that's a nice way of thinking about why it's different, why it doesn't fit into the story that we usually have about sub-Hopf algebras that come from Dyson-Schwinger. But we're not quite in the right notion yet, because if we go down the rest of it, it's all binomial coefficients. It's not all n choose 2s. And so these actually grow faster. So by the definition I gave earlier, it's not a strong second order sequence. But in some important sense, this guy, this most important guy, if I was to use the tree factorial Feynman rules instead of the general Feynman rules, then all this stuff would get zeroed out, and I would only be seeing this one sequence, and it'd be growing quadratically. So there's something importantly quadratic about Convolution that distinguishes it from all the other examples. And I think it also gives us an interesting way of thinking about, of sort of organizing these different sequences, they let us ask some interesting questions and pick out some of them as being like the physical ones and some not. So that was a story I want to tell you. I hope you've had fun listening. Yeah, thank you very much.
Thank you very much. That was nice. So I think we continue with Michael Borinsky's discussion. Then maybe we can have some questions.
All
Michael?
right. So
okay.
Let me share my screen on my iPad. Hope that this works. Looks good. All right.
Okay, great.
Hi, everyone. First of all, thank you, Karen, for the nice talk. And also, I'd like to thank the organizers for this nice conference. I mean, unfortunately, it's just online now, but still, at least there was one day of opportunity to finally speak to people again. And I also want to apologize to everybody. I didn't speak in this one day. I did so in anticipation of the other days where I could still speak to you. So hopefully, there is going to be another opportunity soon. I'd like to draw this discussion and also this little presentation here now a bit more general and perhaps a bit more to like this fundamental viewpoint of quantum field theory. First of all, like the natural generalization or the sort of base case for these rooted tree Hopf algebras, which is interesting in quantum field theory, are these Hopf algebras of graphs, or just algebras of graphs. So in the more general context, we are interested in algebras that are generated by all graphs. So we have something like a Q algebra. It's free and commutative. And the generators are just the plain graphs. And we can make some choices like on the specific classes of graphs which we are interested in, and we can add bells and whistles. And the interesting objects now are certain elements. So I call it now capital X. And these elements are just given as sums over graphs, which are also chosen in some appropriate way. And for each graph, we take the generator for the graph itself, divided by the order of the automorphism group of the graph. And we use a formal parameter, which in Karen's talk was called X. Here, I called it H bar. It depends a bit what your background is, what symbol you use there. So H bar has always sort of a quantum suggestion. If you're more in immersive geometry, you might use Z instead. The parameter which this thing counts is usually the loop number of the graph, or the Euler characteristic, which is almost the same thing. And so in general, what one would like to look into are these power series in this parameter H bar on this algebra H. So these are formal power series in graphs or in trees, like in Karen's talk. So trees are sort of a so these graphs are sort of a stratification of this tree picture, because we can also associate in a certain sense, we can associate trees to each graph, or one tree to each graph. All right. So many of you know that this object can now be promoted to a Hopf algebra, and this is due to Kohn and Kreimer. So the way this works, just very briefly, is that we define a coproduct for each graph, and we sum over all the bridgeless subgraphs of our graph. For instance, bridgeless, so there are also appropriate restrictions. So we have a whole family of different Hopf algebras that we can define this way. So we sum over subgraphs, and we write the subgraph in the first entry of the tensor product, and we contract the subgraph in the original graph in the second entry. And this gives us, in fact, an honest coproduct, and it gives us a bialgebra, and it gives us a Hopf algebra eventually, if we are not too if we fulfill some proper restrictions on these kind of rules with which we select the subgraphs. So an example of such an object, or such an evaluation now. So now we are interested in characters and actual maps from this Hopf algebra. So we are now interested in, we want to go from this Hopf algebra to some other algebra. And we call these now Feynman rules or evaluation maps or something like this. And an example for such a map is exactly this, this character that Karen was talking about. So the renormalized Feynman rules applied to the sum over all graphs. And we can call this evaluation G of H bar and L. As I said, H bar has now the role of X. And L is the is some logarithmic dependence that depends on renormalization. So this character, this map depends on this parameter L. And we want to hit it on all the graphs individually. So this is how this looks like. So we just define this Green's function to be this evaluation of the renormalized Feynman rules for each graph. And we mark each graph with this H bar, where H bar counts the number of loops. So these are the renormalized Feynman rules. Just to go sort of so in this more general context, or why we want to study like these kind of groups and these objects in this context, is that these characters, they are very interesting. They have very interesting properties, and they appear in surprisingly many contexts. And one sort of very powerful property of them is that in the context of this Hopf algebra, they form a group. So we can define this this group product, which Karen also used, which is just given by the convolution of these two characters with the coproduct. And for instance, like Karen also explained already, this renormalization group equation, for instance, demands now a certain structure of these characters. So so these parameters, they have to be additive under this group action. And this group, or the subgroup of this character group, can be interpreted as the renormalization group. And we can also translate this equation now into the target space of our map phi. So remember that phi is, the target space is the space of power series in terms of L and H bar. And in this target space, we find a differential equation. So for these kind of objects, we always have sort of a combinatorial side where the graphs live, or the trees, and we have the analytic side where the power series live. So we can translate these kind of equations into these equations. And in this case, it's the renormalization group equation. And yeah, like I said, this now lives in the target space, but it's usually very helpful to also work upstairs in the original combinatorial space and to differentiate between the two worlds very concisely. And these algebras of rooted trees, they do a very good job to differentiate between these. What I also like to mention is why all this is very interesting is the surprising effectiveness of these kind of characters in enumerative geometry. So it's not only that mathematics is surprisingly effective in physics, but sometimes things in physics are also surprisingly effective in in mathematics. And these kind of characters from quantum field theory are one of these examples. So one of these characters that is very trivial and also very interesting is just the character that associates a -1 for each vertex of the graph. So we map each graph, each generator, to -1 to the power of the parity of the number of vertices. So for instance, phi of this this triple edge graph here is because it has 2 vertices, it's -1 squared, and this rose with 2 petals graph has 1 vertex, so its character is -1. And it turns out if we apply this kind of character already to a sum of all graphs, what we get is very interestingly a topological invariant of a space, namely in this case it's the rational Euler characteristic of an object called the commutative graph complex defined by Kontsevich. So this is due to Kontsevich in 92 and in the context of the theory of these graph complexes in 1994. And using this kind of relationship and by going into this target space and then using quantum field theory methods, we can also evaluate then this character and prove that it's given by negative zeta values, which are just Bernoulli numbers. So we can evaluate it to all this. There are also relations. So you can, for instance, also prove the famous Hara-Zagier formula for the Euler characteristic of MGN using this character and this identification of these maps. There's also another example where you use this this group structure explicitly. So you can look into just for fun, you can look into the character that gives the convolutional inverse of the simple character phi. So we know that these characters, they fulfill a group, so we can also invert a character. And if we compute this inverse and apply it again to this element, to the sum of all graphs, what we get is the rational Euler characteristic out of n. And this is something that we proved in a work with Karen Vogtmann. I also want to mention that these characters are also very interesting in other contexts. So they have some surprisingly universal behavior also in terms of something which we also have heard of in the context of this talk, of this conference, namely resurgence. So in general, these kind of characters can be thought of resulting in some power series in H bar. And we can ask, what's the behavior of these coefficients, of these coefficients for each n in front of H bar? And asymptotically, so for n to infinity, we find that for a very large class at least, these coefficients behave factorially divergent. So we usually think of all these kind of characters here as resulting in some resurgent functions. And yeah, in the great talks by Gerald and the discussion by Frederic afterwards, yeah, we were already seeing this during this conference. Yeah, and one can actually also for simple characters, so for simple evaluations, one can actually prove that one always gets a resurgent function, but it's only for a simple for large. But I mean, large, it's an infinite class of characters, but it's quite simple characters where one can prove this. These kind of Dyson string equations that Karen was talking about today. So I'd like to think of them always as like the quantum field theorist's dream. And I would like to explain this in the last 5 minutes that I still have. So the idea is always to so in this rooted tree case, it fulfills these fixed point equation where we use this B+ operator. And the motivation behind this is, of course, that we would like to formulate something similar in quantum field theories as well. And we would like to study these kind of these fixed point equations in simpler contexts or also in the general context, and categorize the different structures that can appear there. So, but from the perspective of a quantum field theorist, so there's this dream that works by trying to sort of define an operator, which I call suggestively B+, which is an endomorphism on our Hopf algebra or our algebra of graphs. So it somehow maps graphs to graphs. And it should fulfill this Hochschild one co-cycle property, like the normal drafting operator, such that it mimics our nice structure on the rooted trees. So we want to somehow appropriately define such a B+ operator. And this gives us immediately sort of a map from graphs to, it gives us immediately a map from rooted trees to our graphs. And this is something nice that we can have. So we can use all this technology on the level of the rooted trees, also on the level of all the graphs. The next step is to write our interesting element. I mean, the element that interests us as some fixed point equation in terms of this B+ operator now. So for instance, like this, this is also the structure that Karen now had, where we have some kernel F here, which perhaps modifies this, this element still a bit. And in the third step, we want to apply an appropriate character to actually evaluate our X, or to map it in the target space, in some target space that we are actually interested in, where we sort of compute our observables. So we can do this. We can hit both sides of this fixed point equation then with this evaluation map. So on the left-hand side, of course, this is quite trivial. We just get our result. But on the right-hand side, we obtain something interesting. And the fourth step is now just to evaluate this composition of this character phi with the B+ and this kernel in a way such that we can get some differential or integral or recursive equation for our evaluation of our map phi of x for our Green's function. So we want to have some analytic handle on our evaluation phi of x, which is the Green's function, which is non-perturbative in the way that it gives us some generally valid equation in the target space. Where there are many examples that this works. And this is also, so these kind of examples have been the topics of this conference. So in sort of simple, in quotes, Dyson-Schwinger equations, we can make this work. So we can really just, this works by sort of mimicking our rooted tree structures on the level of the graphs, because we can maybe form chains of graphs that are inserted into each other in some well-defined recursive way. And there we can actually make this work and write down differential equations in the target space, which we can solve at all order in principle. And yeah, Gerald was talking about this in the context of our work. This general approach goes back to Broadhurst and Kramer, and also to Karen's work. There's also the chord diagram representation of the Green's functions, which is a realization of this methodology, which is also by Karen and also others. So there also have been many other people working on these Dyson-Schwinger equations approaches, of course. So so this is just very shallow, like these citations here. There are also the instances for the rooted trees, of course, which are also very interesting. And like Karen says, Loïc Foissy categorized these different Hopf algebras, or these different kernels that may appear there in this context. An interesting different, or actually completely different avenue to pursue there, or where I'm actually not which is perhaps more of a question to discuss, is topological recursion, because topological recursion is of course also a recursive way to compute these kind of objects that are graphical and they come from quantum field theories, and ultimately they are also evaluations of certain characters. But the question in this context is, of course, can we also interpret topological recursion in this Hopf algebraic language and ultimately associate topological recursion with a map from rooted trees to these kind of graphs, to actually, because topological recursion, I mean, it gives you a quite general framework to also compute invariance from enumerative topology, enumerative geometry. Of course, and Elba was talking about this yesterday. And the big question here for me is the Hopf algebra interpretation. So one of the big questions, and how this sort of looks, this topological recursion in this Hopf algebra framework, or in this renormalization framework in general. An outlook, which I want to mention as well, is related to Eric's talk on the first day, on Monday. And this is tropical quantum field theory. So in tropical quantum field theory, this quantum field theory stream is also realized in a certain sense. So we can also then really push this recursive structure through to the target space. And yeah, so this is sort of ongoing work in progress, but there has been foundational work by Eric and also work by me already. And yeah, so Eric was also talking a bit about this already on the first day. So I think my time is up. Yeah, thanks again, and happy to discuss with all of you.